All right, 16b is called continuous distributions. A continuous probability distribution, in a continuous probability distribution, the domain of the values is typically from a closed interval on the number line, such as from 0 to 6. There are thus infinitely many values which cannot even be listed. That's continuous, all right? A lot of the things we've been doing before were discrete. So we're talking about whole numbers. What are the possibilities when you roll a dice? We're talking about whole numbers, 1, 2, 3, 4, 5, 6. But a continuous scale, you have all those decimal numbers in between, which is why it's saying there is an infinite number of values that you could have between 0 and 6 on a continuous scale. The probability of any one particular value is 0. And we want to talk instead about the probability, such as probability of an event is between 2 and 5, which is the probability that the value lies between the interval 2 and 5 of the 0 and 6 that we started with. So they're going to talk about some different types of functions in this topic. The first thing we're going to talk about is the probability density function. When you see an equation for probability density function, it will be using the lowercase f. So lowercase f for the probability density function. And we have an example here of f of x is equal to 1 over 18x. And there's even a diagram of it over here between 0 and 6. The probability of being anywhere between h and k is the area under the curve. Okay, so if we wanted to find the probability of that probability density function in a specific area, we would just need to integrate between the parts that we want. Okay, so we have this formula here. The probability of it being between h and k is going to be the integral between h and k of whatever my probability density function is. Okay? Next is the cumulative distribution function. Cumulative, just like in our histograms, means it's adding up as it goes along. The cumulative distribution function uses the capital F of x. So notice we're changing to a capital here, or maybe down there as well. You can see it there in the formula. So the upper case capital F. We can call it CDF for short. So probability density function is PDF, probability density function, and cumulative distribution function is CDF. So the CDF for short of a probability density function is the signed area, which is the integral between a and x, so they're the values that we've been selected on our graph over there. So we're integrating between a and x of our function. Conversely, if you wanted to go from your, sorry, I'm busy trying to highlight extra things here. F of x is equal to the derivative of f dash x. Okay, so let me go back to this one. In this one in here, I'm integrating my probability density function. So you integrate once to find the probability density function. If you're trying to find a specific area, you integrate that function if you're trying to find a cumulative distribution function. Okay, so there could be potentially two integrals that is happening in here. Note, when stating probability density function and cumulative distribution function, density means at a point and distribution means over the range. Uniform and continuous distributions. An important special case of continuous probability distributions is a uniform continuous distribution. This is a distribution where the PDF is constant, which would be a horizontal line. Okay? Because the area under the graph, probability would always be equal to 1. A uniform continuous distribution is defined over an interval, if you're using A and B, whatever those values are on your particular case, then it would be y is equal to 1 over b minus a. Distributions with unbounded domains. In many important situations, the probability density function has a horizontal asymptote. However, this means that it is possible for values to extend infinitely. So we don't have any set endpoints, which makes things tricky. Okay, what are we going to do? Here we go. Question 1. Bob does not know the times when the trains leave Gosford Station, but he does know that they leave precisely every 15 minutes. He wants to know about the probability distribution of his waiting time if he arrives at the station at a random time, and what the PDF and the CDF are. They're the two different types of functions. Okay, so if he knows that a train has to leave every 15 seconds, that means, every 15 minutes, sorry. Every 15 minutes, I didn't even notice. That means that my PDF, the maximum time that he could have to wait would be 15 minutes. So he could arrive just when the train has left, and he might have to wait a full 15 minutes for the next one to arrive. But it could be anywhere in between that, right? So I could draw a graph of what this is going to look like. There is a maximum here of 15 minutes, this is the time axis that he would have to wait. And on the vertical axis, this is going to be the graph of the PDF, the probability density function. This is a continuous function. There would be a 1 in 15 chance for that graph, for the probability for that train to be arriving. To draw it, it's going to be a constant like that, and this here would be a 1 over 15. That means that the probability, the area underneath that graph there is 1, because 15 times 1 over 15 makes a probability of 1. Okay, so that's my PDF. That's between 0 and 15. The CDF, the cumulative one, which is using the capital F, means that I would need to integrate the lowercase f of x. So I'm going to integrate 1 over 15 with respect to time between the 0 and I'm going to say between 0 and x because it's cumulative. I don't want it, I want this to be for anywhere along the way. Okay, I'm not saying that it's definitely going to be at 15. I'm saying for an equation that would represent any time, x is going to be my variable in that. Okay, so integrating, I get t over 15 because t is what I'm integrating with respect to because it was a dt. And I'm subbing in between 0 and x. When I sub that in, I get x over 15 minus 0 over 15. So 0 over 15 doesn't do anything. And the equation of my graph would just be x over 15. If I want to draw that, that's still a straight line, but it's now a sloping straight line that has a gradient of 1/15. Okay? The intercept would be at the origin, because thinking of if it's cumulative, it makes sense, it's going to start at 0. And if I show a point on here, I could show 15, for example. If I subbed 15 into my equation, 15 over 15 makes 1. So the height of that at that point would be at 1, and I would have a line like that. Okay, so they are the two different equations and the graphs that go with them. Part B, he also wants to know the median and the 45th percentile and the probability that he will wait between 5 and 10 minutes. Now, let's start with the median. Median means the middle. If I'm using my cumulative frequency, I need to find the middle of it, which the time-wise I've got it's going up to 15 because we knew it was a maximum of 15 minutes for when our next train could arrive. So the middle of that's going to be at 7.5. So let's write that down. We're going to have the median. It would be when the cumulative function is half, okay, because on the vertical axis, my scale was 1, so half of that is 0.5. But if I put that into my formula, I get, it was f of x equals x over 15, so it would be 0.5 equals x over 15, which is how I get the 7.5. Okay, basically, in other words, here's my 0.5 on that axis. I go dot, 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 dot across. I've subbed it in, and that value there would be 7.5. That's my median. Now I have to find the next thing, which was the 45th percentile. That means that's a probability of 0.45. Okay, percentage out of 100. So as a decimal, that's 0.45. So 45th percentile means that the cumulative f of x is going to be equal to 0.45. Okay, let's do what I did last time. I'm going to sub that into this capital F of x equation over here. Okay, that is 0.45 equals x over 15. So what does x equal? Times the 15 over. 0.45 times 15 is 6.75. Okay, so the median time that he would have to wait is 7.5 minutes. The 45th percentile means that he's waiting 6.75 minutes. Okay, there's still more. It says, what is the probability that he will wait between 5 and 10 minutes? Okay, so let's write this down. Probability that the wait is between 5 and 10 minutes. There's two ways you could do this. Notation-wise, you would write this as the probability of my event is between 0 and 10. It's notation, okay? I could do this as an integral. I could put this into an integral here where I'm integrating between 5 and 10, and I'm integrating the PDF function 1 over 15 dx. Okay? If I integrate that, sorry, not an integral sign, square brackets. If I integrate that, I get the x over 15, which is my cumulative frequency, but I put on here between 5 and 10, and then I'm subbing those values in. So subbing in 10, I get 10 over 15 minus 5 over 15, and that is a 1 in 3 chance, or a 0.33 or 33% probability that he's waiting between 5 and 10 minutes. The other option is, so this is method 1, sometimes more options is not always a good thing, is it? So method 1, method 2. For another option, same notation, I want the probability that is waiting between 5 and 10 minutes. Instead of integrating it again, I already know what my cumulative distribution density function is. So I could just sub straight into the capital F, f of 10 minus f of 5. Okay, so again, that's back to if my f of x equation up here is this one, you're subbing straight into that. So it is back to 10 over 15 minus 5 over 15, and you get the same answer of a third. Okay, so what you're doing is you're finding the area between 5 and 10 on here. So 5 would be there, 10 could be there, and you're finding that area, that space under there. Anyway, okay, let's go to question 2. Find the value of k that makes f of x equal k, where x is between 0 and 10, a probability density function. Then find the corresponding CDF, or capital F of x, hence find the median and the quartiles. Okay, starting with the PDF. We are told that the function f of x, lowercase f of x, is equal to k. So I know that if I integrate k with respect to x, that would be the PDF function. This particular question has a domain there between 0 and 10. So it gives me values to integrate between. The other thing that I know is because this is a PDF, the area underneath it must always be equal to 1. Probability, area must be equal to 1. So I can say that that integral must be equal to 1, which enables me to work out what k is. All right, so let's integrate. Kx between 0 and 10 is equal to 1. Subbing in. I'm subbing that into the x, okay, that's what we're integrating. So it is 10k minus 0k, which is just 0, equals 1, so I don't need the 0. And when I divide by the 10, I find out that k is equal to 1/10. This means that instead of having an equation for lowercase f of x as a k, I now know what that k is equal to, which means that that is equal to 1/10. There's my PDF. Now I have to find the CDF. There's still a fair bit to go here, so don't use your space up too quickly. To go from the PDF to the CDF, what do I have to do? Integrate it, okay? So capital F of x means that I'm integrating, this is the formula, you're integrating the lowercase f of t with respect to time. And what you're going to do is you're going to go between 0 and x, so that what you're going to get out of it is an equation of x that represents the cumulative density function. So in this integral, we're going to put in here the f of t is 1/10. And we're integrating it with respect to t, which means that will become t/10 between 0 and x. Capital F of x equals x/10. All right, I have found my two functions. Now I need to find the median and the quartiles. Median is the middle of the capital F of x. Okay, because it's cumulative. So you find the middle, which is going to be when f of x, capital F of x, is equal to 0.5. If you put that into your equation, you'll get 0.5 equals x/10, which means that x is equal to 5. The median is 5. Quartiles. So that's the Q1 and the Q3. If the median is 0.5, what's Q1? 0.25. It's the lowest 25%, right? Very good. So Q1 is going to be when f of x is equal to 0.25. And Q3 is going to be when f of x is equal to 0.75. And you can still then solve them the same way as we did the median. So it will be 0.25 equals x/10. So x will be equal to 2.5. And 0.75 equals x/10, which means that x is 7.5. Okay. We're out with that. Moving on. We've got a lot to get through. Question 3. Find the value of k that makes lowercase f of x equal kx, where x is between 0 and 10. It needs to make a probability density function, which means that that would have to be equal to 1. I'll have them finding the values of k that will make that a probability density function, and I will do that by making the equal to 1 and solving for k. All right, so PDF means my f of x is kx. I'm going to integrate with that with respect to x between 0 and 10 because those values weren't negotiable. It's all about what is the value of k that makes that a PDF. In your exercise, there's quite a few questions that will ask you, is this a PDF? And the way to know that is whether when you integrate it, it makes 1 when you evaluate it. If it doesn't make 1, it's not probability. Probability should always add to 1. The other criteria is that you can't have negative probabilities. So if your graph, if you were to sketch it, if it gives you a full equation, not something with a k in it, but if you got a graph where you know that graph in the domain you've been given is below the x-axis, that's indicating negative probabilities. Can't have that. So that would not be a legit probability density function. Okay, so they're your two things you look for in a PDF. Okay, let's integrate to find out what k is equal to. So integrating the x, I will get kx squared over 2 between 0 and 10. That has to be equal to 1 for it to work. Okay, and now I'm going to find what k is to make it work. So let's sub in. K times 10 squared is k times 10 squared over 2 minus k times 0 squared over 2 is equal to 1. Okay, obviously that whole second thing there is 0. 10 squared is 100, so 100k times the 2 over to the other side is equal to 2. Then dividing the 100, 2 over 100 is equal to 1 over 50. So the value of k that makes that a probability density function is 1 over 50x. Now that I have that, it says, then find the corresponding CDF. Cumulative. We want the cumulative function. So let's go back up here. CDF can be found by integrating. Capital F of x is found by integrating. We call it f of t. So we're putting in an extra parameter there so that we can sub our x back in, okay, between 0 and x. That's the formula. That's a formula that I'm writing down there. So you can kind of use that every time. So for our case, we have 1 over 50. Instead of x, we're calling that t, dt. And we are integrating that with respect to t. So t squared over 100 between 0 and x. We can't, that's why we need the t in there. We can't integrate x and then sub x back in. We have to change the letter in there so that we can work with that. Subbing in x squared over 100 minus 0 squared over 100, so that would just be 0. So that there would be my capital F of x, my cumulative function. Hence, find the median and quartiles. We get to practice that again. Same as what we did in question 2. The median will be found when the cumulative function is equal to 0.5. Okay, so be at 1 when it's at the end, so half of that is always 0.5. So I'll have 0.5 equals x squared over 100 times the 100 over, that would be x squared equals 50. And then square root of 50 in exact form, not decimal, is, isn't it 5 root 2? 5 root 2. Then the quartiles, Q1 is when f of x is equal to 0.25, and then the Q3 is going to be when f of x is equal to 0.75. Sub those in and find what values they are. So 0.25 equals x squared over 100, x squared equals 25, x is equal to 5. Should it be plus or minus? No, why not? Well, first of all, look at the domain. The domain up here was between 0 and 10. You can have negative values for x. You can't have negative values for the probability of it. You can have scores that are negative, okay, but the probability of it can't be negative, so it can't be below the x-axis. But in this particular domain, it does say that it needs to be between 0 and 10, so I'm only taking the positive version because the other one is not in the domain that we're looking. Solving the other one, 0.75 equals x squared over 100. So x squared is equal to 75, and the square root of 75 is 5 root 3. Okay, question 4, to make it a little bit more. A probability density function is defined piecewise by that lovely equation there. So they're saying there's two separate equations depending on the x value. Anytime that x is between -4 and 0, we would use that equation. When we're between 0 and 4, we use the second equation. We've seen functions like this before. We just haven't necessarily integrated them. Here we go. We need to find the value of the constant that would make that a PDF, which means that its area would be equal to 1. Okay? It says, and hence write the equation of f of x and sketch it. Okay, this will be a big thing, right small. The PDF can be found by integrating. We're going to have to do two integrals because we have two sections. We're going to integrate between -4 and 0, the first equation, which was k bracket 4 plus x. K is just a constant, just sitting in there, and I need to find out what it is. Then that would give me part of the graph. That would be part of the area, which would be contributing to the probability of 1. I would want to add to that the section from 0 to 4, which has the equation k4 minus x dx. Those two integrals from those two sections that are making a graph, those two areas will have to make a probability of 1. And I will integrate them and solve them and find out what k is. All right, to integrate them, probably don't want the brackets in there. So let's expand out the brackets first. -4, 0, it'll be 4k plus kx plus 0 and 4, 4k minus kx. All right, to integrate, square brackets. Remember k, I'm not integrating the k. 4k is just a constant. When I integrate it, it will become 4kx. It gets an x added to it because it was a constant. The kx, it already has 1x. I need to add 1 to the power and divide by the power. Kx squared over 2 between -4 and 0. Plus, do the second one. 4kx, so it gains an x because it was a constant, minus kx squared over 2. That's between 0 and 4 and will be equal to 1. Okay, subbing in. When you sub 0 into that first square bracket, is there going to be anything left? Because 4kx has an x in it. So if you times the 0 in there, that's 0. Kx squared over 2 has an x in it, so that's equal to 0. So subbing 0 in is just going to give you 0. Then you have to minus and sub in the -4. I'm going to put this in brackets. So it would be 4 times negative 4, which is negative 16k. Is that all right? Then plus the x squared would be minus 4 squared, so that's 16k over 2. Oh, I'm going to change that to 8k, like that. All right, plus, second one, subbing in the 4, we get 4 times 4 is 16k, minus 4 squared is 16 over 2, 8k. But then I have to sub in the 0. Is subbing in the 0 going to give me anything? No, it's going to be minusing 0 off, so I don't really need that. So I'm going to close that off, and that's going to be equal to 1. Okay, now see that first bracket? I have to be careful with those minus signs. That minus at the front needs to come in. So I would get a positive 16k minus 8k. 16 minus 8, that's a plus 8k, is equal to 1. Oh, they just cancel out. I just get 16k equals 1, which means k is equal to 1/16. The minus sign in that first bracket had to expand through, so it became a positive 16k and a minus 8k. But then the second bracket, 16 minus 8 makes a positive 8, which is how that negative 8 plus 8 cancelled out. Or you could have done it all in one line, if that worked. Okay, I'm still not quite done with part A, because it says, hence write the equation of f of x. And sketch it. So my equation of f of x, if I look back to my yellow stuff up the top there, f of x equals, big funny brackety thing, k is 1/16. So it'll be 1/16 4 plus x. That's between minus 4 and 0. And it would be 1/16 4 minus x between 0 and 4. Ready to draw? Yes, yes. I only heard yes. Okay. Between 0 and minus 4. 1, 2, 3, 4. There's my minus 4. Here's my 0, the origin. My equation is 1/16 4 plus x. Okay, if you wanted to, that was how it was in the question. A 16th of 4 would be a quarter plus 1/16 x, if I expanded it out. Does that help? Huh. Okay, that means, what is my y-intercept of that? A quarter, right? So my graph is going to come up here to a quarter. That's going to be the intercept. What kind of line is, what kind of graph is that? What's a line? Okay, so I just need to know what's happening at minus 4. So that's where I'm on my other extreme. So if I sub minus 4, let's sub into the purple one. 4 minus 4 is 0. So 0, if I'm subbing into here, 0 times 16 is just 0, so it's going there. That is a line down there. That is the line of the top one, the graph of the top one. The graph of the second one, let's do the same thing. Let's just sub in. If we subbed in 0, we would get 4 minus 0. That's 4 times the 16. There's my quarter again. So it's still here at a quarter at 0. And then when you go 1, 2, 3, 4, sub 4 in, 4 minus 4 is 0. So it's going to be down here. And that is the graph. Told you could have negative x values. Okay. Part B. Oh, and we've still got like 3 more pages to go. Part B. What is the probability that x is between 0 and 2? So this is probability that x is between 0 and 2. What do? Probability is going to be the area between 0 and 2, if this is a PDF, which means I can integrate between 0 and 2 the equation of my PDF. Now, there's two different equations. Do I need both of them? No. Which one do I need? I need the one that's between 0 and 2, which is the second one. So 0 and 4 is only in the bottom one there. So I'm going to integrate the 1 over 16 4 minus x dx. All right, integrating. Let's just put the 1 over 16 out the front. And then get 4x minus x squared over 2 between 0 and 2. Sub in 1 over 16. We have 4 times 2 minus 2 squared over 2 minus, what happens when I sub in 0? Just 0, so it does nothing. Let's get rid of it. And that equals 3 over 8. Okay, so the probability of it being between 0 and 2 is 3/8. Why is the median 0? And what is the mode? Okay, anyone want to try to explain the median part? The median is the middle, right? So if that's my probability, this is not cumulative, so I'm not carving spaces or anything. This is not the cumulative one. But if I want the middle and my scores are going between -4 and 4 and it's perfectly symmetrical, the median is going to be smack bang in the middle, which is at 0. Okay, so let's write that down. Sorry? Oh, no, I thought you said something to me. All right, the area to the left and right of x equals 0 are equal. So we're saying it's equal on both sides, so that means that the median must be 0. What about the mode? Which score, if those things across the bottom were the score, which thing is happening the most? 0. It has the highest point, right? So the mode is also equal to 0 because it is the global maximum, the highest point of the PDF. All right, part C. Guys, find the CDF between -4 and 0 and between 0 and 4 and sketch the whole graph. Put it all together, basically, at the end. All right, we're going to call this capital F of 1, the first one. Well, the first one and the second one. The first one, we are going to be integrating. Now, normally it says my domain is between -4 and 0. So the bottom number is always your starting point, and all the other ones it was 0 because we were having graphs that were starting at 0 and going on from there. This one's starting at -4, and I want to accumulate it to some point that we're going to call x. Okay? I'm going to integrate the function, which was 1 over 16, and we're just changing it into t, so 4 plus t, and we're integrating with respect to time so that we can put the x back in. Okay? When I integrate that, I have 1 over 16. I'm just going to slide that out the front. Integrating the 4, I will get 4t plus t squared over 2 between -4 and x. And then we have to carefully sub that in and get our equation. So I'm going to, oh, that's a 16, sorry. There's an extra 1 on that. So 1 over 16 at the front. Subbing in x, I get 4x plus x squared over 2. Minus, sub in -4 would be -16. So I put brackets in there because I've got multiple negative signs happening. -16 plus negative 4 squared is 16 over 2, or just 8. Close bracket, close bracket. Okay, tidy it up, tidy it up. What have we got? 1 over 16. We have 4x plus x squared over 2. 16 minus 8 would be a plus 8. And if I don't like that fraction out the front, we could times the fraction through now. Put that 1 over 16 through. So 4 over 16 would be x over 4. Then x squared over 32, because you're timesing the 16 and the 2 together. They're both in the bottom. And then plus 8 over 16 is a half. Okay. To help me draw this, should I do it now or later? Maybe I'll do it later. Don't worry, I'll do that in a minute. I will come back to that. F of 2. Second one. Do it all again. Wait, chatterboxes. Do this, please. We are going to integrate the second one, which is between 0 and 4, but we're going to start at 0 and go to x, because we're accumulating. What's it as it accumulates? Of 1 over 16 for minus t, we're changing into t, dt. Now, there is an extra catch here. If this has to add on to the last graph, how much probability has already happened? Was this too much? How much probability has already happened in the first one? Half of it. So we need to add on to here a half. If I'm going to draw this as a cumulative frequency graph, okay, the f of 1 is the first 50%. We know it's symmetrical. Okay, we know it's perfect on either side. That's the first 50%, the f of 1. If I'm going to add on the f of 2 graph onto that, I'm not starting back down at 0 again, even though that's where I'm integrating from. That's not the point. But it needs to add on to the last graph, which was already 0.5 probability in. Okay? All right, so now let's integrate that. Leave the 16 out the front. We have 4t minus t squared over 2 between 0 and x, and we have our plus half sitting at the end. Then we have got, subbing in, 4x minus x squared over 2. If we sub in 0, we get 0, so that's nice, plus a half. Expanding it out, 4 over 16 would be x over 4 minus x squared over 32 plus a half. So that would be my equation of my f of 2. Okay, I need to draw these now. I found them. Now let's draw them. Okay, maybe over here on the side. You don't just have random space at the side of your page? Sadly, no. Okay, minus 4 to 4. And we know this is cumulative, and it's going to come up here to 1. Cumulative, the probabilities have to add to 1. Okay, so that's, and half is important because we know that our first graph is going to end there. Okay, so between 0 and minus 4 and 0, we know it's going to end here at a half. We should be able to check that by subbing in 0 into that equation over there. And it would work. If you subbed in x equals 0, the number on the end is a half. It works. Okay, what happens if you subbed in minus 4 into that? Or can you guess what it would be, given this is a cumulative frequency graph? 0. So it's going to start here. Now, is it going to be straight between those two crosses? No, because what kind of graph is that? It's not very nice, but it's parabola. Is it concave up or concave down? up. So it's going to come up something like that. Then we switch and we come over to f of 2. F of 2 at 4. When we're at 4, where's it going to be? Where should it be even without subbing in? 1. No, 1. Because it's at the end. So that's up here. Sub it in. You can always sub it in. You'd sub 1 into your equation and you should get, sub 4 into your equation and you should get 1. But this is also a parabola, but it's concave down parabola because it's negative on the x squared. So it's going to go like that. And that is the graph of that. Okay, let's keep moving. Question 5. The radioactive isotope, here we go. Is it chemistry? Chemistry time? The radioactive isotope iodine 131 is often used in medicine for the treatment of thyroid cancer. It has a half-life of about 8 days. Suppose that we isolate a single nucleus of iodine 131, observe it constantly, and record the time x in days, before it decays. What's up with you? Don't you like this question? Shh. Listen. Let f of x be the PDF. Capital F of x is equal to 1 minus e to the negative kx. So we've advanced into exponentials here now. Where k is equal to 1 over 8 ln of 2. Let the CDF for the scenario above, observing time x days that iodine 131 nucleus survives before decaying. Where's all the scientists in the room? Do we love this question? No, we don't like this question. Okay. Explain. Oh, it gets better. Explain why the domain of possible values is unbounded in the interval 0 to infinity. We're talking about an exponential, which when you're talking about isotopes and decay, they are on exponential curves. So this is a fairly standard kind of question. But if it's an exponential graph, we know that exponentials are approaching asymptotes, right? They will never completely reach 0, depending if it's coming down. It's never completely going to decay down to nothing. Okay? So let's explain this by starting with our CDF equation, which is 1 minus e to the minus k of x. Okay, what I want to do, if this was bounded, it should be able to get to a total probability of 1. Okay, because it's like that last one that I did. When it's bounded, it should be able to get all the way to the top of that cumulative graph, which has a probability of 1. Can I do that for this one? If I make f of x equal 1, I get 1 equals 1 minus e to the minus k. So maybe write in here, see if the CDF can ever get to 1. Okay, I'm going to try and solve this. When I solve it, if I move the 1 across, I get 0 equals minus e to the minus kx. I could get rid of the minus, but if I tried to do a sliding base on that, I would be having log base e of 0, which does not exist. So there's no solution to that. So we can write down here no solution, which means that my graph has to be unbounded because it goes on forever between 0 and infinity. Square bracket means inclusive, infinity round bracket because it's not a real number.
Is that supposed to be a C?
That's a plus.
Oh.
That one there. It was my minus sign, and I said we could just get rid of the minus sign, so I turned it into a plus. Yeah, so I can just get rid of that. There like that. Okay, next part. Boys, if you don't want to listen, please go and waste time somewhere else. Go and sit outside. But if you want to learn, please be quiet. Pay attention to the lesson. Part B. Find the formula for the PDF and sketch the CDF and the PDF. Okay, the formula for the PDF. We haven't had this happen yet. I've actually got the cumulative one and I'm going to have to go back to find the PDF. How should I do that? Differentiate. Good. So PDF equals. So I'm going to differentiate the F, capital F of X. So that will give me little f of X equals, look up here, there's my capital F of X. When I differentiate it, the 1 will disappear. The exponential part, the minus k will come down. With the minus that's already at the front, it becomes positive. K e to the negative kx. Okay, that would be the equation. However, I do happen to know what the constant is. Remember back here, constant k is equal to 1 over 8 ln of 2. So I could sub that in as well because I have to draw it. So I'm going to have to need to know that if I'm going to draw it. So it's going to be 1 over 8 ln of 2 e to the negative 1 over 8 ln of 2 times by x. That is gross. How can I fix it? PDF of this graph, we need to put the x on the horizontal axis, f of x on the vertical axis. We're going to sketch the graph of the one in the pink box, which means we're drawing an exponential graph. If I were to sub in that x was equal to 0, the exponential part would become equal to 1, which means that my intercept here will be at k. Then, because of the negative power on the exponential, it is going to be decreasing and approaching a horizontal asymptote of y equals 0. We also want to draw the CDF of this graph, which would be x on the horizontal and capital F of x on the vertical. The equation for this one was 1 minus e to the minus kx. If we were to sub in that x was equal to 0, then the exponential would be equal to 1. 1 minus 1 means my graph is starting at the origin. This is also an exponential graph, and it's going to be approaching the asymptote of y equals 1. So it's going to come up like that. So they're the two graphs. Next, we need to find the median and the half-life. The median is when the cumulative function is equal to 0.5. If I sub that into my equation, I have 0.5 equals 1 minus e to the negative kx. Minusing 1 from both sides, I would get negative e to the negative kx equals negative 0.5. We can cancel the minus signs off though, and then do a sliding base. So negative kx equals ln of 0.5. X would be equal to ln of 0.5 over negative k. Now, if we want that as a value, we're going to have to sub our constant in back up here. K is equal to 1/8 ln of 2. So ln of 0.5 over 1/8 of ln of 2 gives you that x is equal to 8. Okay, there's my median. Find the probability that it decays, find the probability that it decays on the first day and after the first day. So on the first day would be the probability that x is less than or equal to 1. To find everything less than 1 would mean I want the cumulative. I could use the cumulative equation and sub in the 1. So that would be 1 minus e to the negative, I'm putting in my value of k in here, and times 1 for the x value that I'm subbing in. That's equal to 0.083. Hence, or otherwise, if I wanted to find the probability that it decays after the first day, I would want to find probability of x is greater than 1, which would be, because the probabilities have to add to 1, I could just do 1 minus the 0.083 that I just found, which makes 0.917. Question 6. Find the shaded area under the curve y equals 1 over x squared over the interval between 1 and infinity. The graph of this is hyperbolic in the first quadrant, but because it's x squared, it's in the first two quadrants. It looks like that. I'm wanting the area from 1, so if I draw a dotted line there, all the way to infinity, so everything is going all the way up there. Area will be equal to the integral from 1 to infinity of the 1 over x squared dx. Integrating, I can't do it while it's a fraction, so let's bring that up to be x to the minus 2 dx. Now I can integrate it by adding 1 to the power and dividing by the power. Let's tidy it up a little bit. That would be the same as minus 1 over x between 1 and infinity, which means I have negative 1 over infinity minus minus, so plus 1 over 1. 1 over infinity is basically equal to 0, plus 1 means that that is 1 unit. So the area under that curve is 1 unit squared. Part B, hence show that y equals 1 over x squared for x is greater than or equal to 1 is a PDF, and find the CDF. So since the area was equal to 1, that is why it's a PDF. Also, the graph is above the x-axis, so that's an important criteria. So I'm just going to write down here, since the area from 1 to infinity is equal to 1, it is a PDF. To find the CDF, we are going to have to integrate the PDF, which is, the equation was 1 over x squared. We're going to make that 1 over t squared, so we can integrate it with respect to t between 1 and x, because we're starting at 1 and going on from there. Integrating, well, actually before I integrate, I need to bring my power back up. So it will be t to the negative 2 dt. Adding 1 to the power would be negative 1 over negative 1 between 1 and x. Putting it back into nicer form, we would get negative 1 over t between 1 and x, and then subbing in, we get negative 1 over x minus minus, which makes plus 1 over 1, which is 1. So that would be the equation of the CDF. Question 7, show that the improper integral between 1 and infinity of 1 over x does not converge to a limit. So this graph is a hyperbola. The x isn't squared this time, so we're in the first and the third quadrant. If I wanted the area from 1 to infinity, that would be the bit there that I'm trying to find. And I could find it by integrating. Integrating between 1 and infinity of 1 over x dx. Integrating 1 over x becomes a logarithm, so that's ln of x between 1 and infinity. And when you sub in, you get ln of infinity minus ln of 1. ln of 1 is just equal to 0, so that will disappear. and we get ln of infinity. Now, that ln of infinity, or an infinite number, is definitely not converging, because it is getting bigger and bigger as the value is getting bigger. A logarithm looks like this. So log of a very, very big number is still getting bigger and bigger and bigger. It's not stopping. So we're going to say, therefore, it doesn't converge to a limit. It's not approaching an asymptote. It will continue to get bigger forever. Okay, that's the end.